All right, in this lesson, we are going to graph rational functions that have holes in them. And so a quick recap is when we are looking for key attributes of rational functions, if we want the x-intercept, we set the numerator equal to 0. So say we're talking about some rational function that has a numerator function and a denominator function. And so the x-intercept is the x value where the numerator is equal to 0. And it's an ordered pair. The vertical asymptote is where the denominator equals 0. And it's an x equals equation. So I call these like the x things. One's an x equals equation, that's your vertical asymptote. The other is an x-intercept, that's an ordered pair. The x-intercept is where the numerator equals 0. The vertical asymptote is where the denominator equals 0. That's because it makes the function undefined. And so what we haven't talked about is what happens if you have the same factor in the numerator and denominator. And so, for example, let's say I had x plus 3, x minus 1 on top. And let's say I had x plus, let's do a minus again. Let's say we had x minus 5, x minus 1 on bottom. Okay, well, we know there is going to be an x-intercept at -3, 0. And we know there is going to be a vertical asymptote at x equals 5. And so the question is, what is happening at x equals 1? On one hand, we'd want to say it was an x-intercept. On the other hand, we'd want to say it was a vertical asymptote. And it can't be both. And so what happens is there's actually a hole at x equals 1. And so in general, if the numerator and denominator of a rational function have a common factor, in this case I'm talking about x minus 1, the function will have a hole at the x value that makes this factor equal 0. And so that's where I got the x equals 1. Okay, so in general, if x equals a, some number a, is where the hole is, when you plug that number in, you're going to get 0 over 0. So for example, if I were to plug in 1, I would get 0 over 0 for this example. And so when we simplify it, meaning we cancel that common factor, we end up with a rational function that no longer has that problem. And so when you plug in the 1 to this simplified form, you don't get 0 over 0 anymore. For this example, you would get 4 over -4, which is -1. And that is the y value of the hole. So when you're writing a hole, it's kind of like a point. It's an ordered pair. And so we would say there is a hole at 1, -1 for this example. Another name for a hole is a point discontinuity. Discontinuity. Some call it a removable discontinuity. Because unlike an asymptote, it doesn't really change the behavior of the graph. You just skip right over it and act like it wasn't there. And so when you are graphing rational functions, you want to factor everything in sight, but it's often easier to find the y-intercept and the horizontal asymptote before you factor. And so the order I like to go in is find the y-intercept and horizontal asymptote first. Those are the y things. Then factor the numerator and denominator, and identify any common factors. That's where the hole will be. And so once you find the coordinates of the hole, that's when you're gonna start finding your x-intercepts and your vertical asymptote. The important thing is you wanna find the x things last. And so you want your x-intercept last, and you want your x equals asymptote last after you get rid of the hole. Otherwise, you're gonna say it's an x-intercept, and then you're gonna turn around and say it's a vertical asymptote, and that's not the case. It's a hole. It can't be all of these things. Okay, and so let's do some examples. And so following this order, we're gonna find the y-intercept and horizontal asymptote first. Okay, and so the y-intercept is when we plug in x equals 0, and so all of our x terms disappear, and so we end up with just -5 over -25, which simplifies to positive 1/5. And so the ordered pair for the y-intercept is 0, 1/5. Okay, and then for the horizontal asymptote, remember that's the ha, funny acronym. And so this is where we look at the degrees. And so here we have a degree 1 over degree 2. So it's bigger on bottom, and so that's the Bobo case. And so y equals 0 would be the horizontal asymptote. Make sure you include the y equals, otherwise we don't know it's a horizontal line. Okay, and so we can put these on the graph. At y equals 0, we have an asymptote, a horizontal asymptote. And then at 0, 1/5, we have the y-intercept. So that's really close to the asymptote. All right, next, this is when we want to factor. So on top, there's really nothing to do. It's just a linear factor. So I'm going to go ahead and put it in parentheses to show that that is a factor. And then on bottom, that's a difference of squares that factors to 2x minus 5, 2x plus 5. Okay, and so once you see a common factor, I cross it off and then immediately write the word whole. And that factor that I just crossed off, that's the factor I'm setting equal to 0. That's where the whole is going to be. And so when we solve this, we get 2x equals 5. Divide by 2, we get x equals 5/2. So that's the x coordinate of the whole. To get the y coordinate of the whole, we have to keep simplifying. And so after that common factor is gone, I end up with 1 over 2x plus 5. There's nothing left on top, so there's a 1 as a placeholder. And from now on, we're using this simplified expression. Don't go back to the original. And so to find the y value of the whole, we take that simplified expression, 1 over 2x plus 5, and we put the 5/2 in for the x. And then when we simplify, 2 times 5/2 would just give us a 5. And then in the denominator, 5 plus 5 is 10. And so the ordered pair for the whole is 5/2, 1/10. And 5/2 is 2.5. And so at x equals 2.5 and y is 1/10, that's really close. And so you graph it just like a open circle. It's like a point, but open. That's what a whole looks like. Okay, now we're at step 4, which is we're using the simplified form to find the x things, the x-intercept and vertical asymptote. And so for the x-intercept, that's where the numerator equals 0. For the vertical asymptote, that's where the denominator equals 0. That's why you want the common factor gone, otherwise you're going to say it's both. Okay, so our numerator is just a 1. And when you set that equal to 0, there's no x there, and so there's no x-intercept. For the vertical asymptote, we set the denominator equal to 0. And so subtract 5 from both sides, and then divide by 2. And so we get x equals negative 5/2 for our vertical asymptote. And so that's negative 2.5. So about right here would be our vertical asymptote. And then we don't have an x-intercept to graph. Okay, and so this graph, we can kind of see what it's looking like in the right quadrant. It's going to go down towards the green asymptote, and you kind of treat the hole as if it were a point. It's still going to go right by there. And so we don't know what's happening over in our left quadrant. We don't know if the function is above the x-axis or below the x-axis. And so that's when we want to choose a test point to the left of this asymptote. And so maybe -3. You could pick -4, -5, -6. I like to stay as close to the asymptote as possible. And so I'm going to plug in x equals -3. And again, we're working with the simplified form. And so our simplified form is 1 over 2x plus 5. And we're putting in -3 for the x. And so that gives us 1 over -6 plus 5, which is 1 over -1, which is -1. So another point on our graph is -3, -1. And so we know there is a point right here. And so the rest of the graph is going to be over in this bottom left quadrant. Okay, so remember your vertical asymptote divides your graph into branches. And so we have 2 branches, one on each side of the asymptote. Last thing is the domain. And so we have 2 domain restrictions. You honestly didn't even need the graph to do this. Your domain restrictions are where the denominator equals 0. And so we still have to skip over the vertical asymptote. And then now the other thing we are skipping over is the hole. And so when we write this, go from left to right. And so -infinity until we reach the asymptote. And then we pick back up on the other side of the asymptote. And then we get interrupted again at the hole. And then we go on to positive infinity. So we're skipping over 2 values. One at the asymptote, so -infinity to -5/2. That's the vertical asymptote. And then we pick back up on the other side. And then before we get to positive infinity, we get stopped at the hole, which is at +5/2. And then pick back up on the other side and go to positive infinity. And so remember, always use parentheses because you don't equal these values. And so this first thing we're skipping over is the vertical asymptote. The second value we're skipping over is the hole, both because they make the denominator equal to 0. Okay, in this next example, before we factor, we're going to find the y things. So we're going to find the horizontal asymptote, which is our y equals equation. And then we're going to find the y-intercept by plugging in 0 for x. And so for the y-intercept, this would be 0, this would be 0, and this would be 0. And so that leaves me with just a -1 on top and a 1 on bottom, which is -1. So our y-intercept is 0, -1. For the horizontal asymptote, we look at the degrees of the numerator and denominator. And so here we have degree 2 over degree 1. And so this one's bigger on top. And so that's the bottom part. And so that means there's no horizontal asymptote. Okay, and so after that, we need to factor And so to factor the numerator, we have an added step because a isn't 1. And so 2 times -1 is -2. We need two numbers that multiply to -2 but add to +1. That would be 2 and -1. And so split the middle with those numbers. 2x squared plus 2x minus 1x minus 1. We can factor out a 2x. Factor out a -1. So x plus 1 is one of our factors. 2x minus 1 is the other. And so this factors to x plus 1 times 2x minus 1 over x plus 1. And so we have a common factor with the x plus 1. And so immediately we know there's a whole. And that factor I crossed off was x plus 1. That's what I'm setting equal to 0. And so that means the x value of the whole is -1. We keep going, and we end up with an expression that doesn't have a denominator. And so 2x minus 1 over 1, we're just going to write it as 2x minus 1. That's a linear function. So when we graph this, it's going to look like a line with a hole in it. Okay, and so we still need to find the y value of the whole. And so y equals 2x minus 1 using the simplified form. And we put the -1 in for the x. And we end up with -2 minus 1, which is -3. So -1, -3 is where the whole is. Okay, and so we can put this on the graph. -1, -3 would be down here. That's the whole. And then 0, -1 would be our y-intercept. And now we're ready to find the x things. Okay, and so we are looking for the vertical asymptote and the x-intercept from simplified form. And so for the vertical asymptote, we set the denominator equal to 0. For the x-intercept, we set the numerator equal to 0. Well, this function has 1 as the denominator. And so when we set 1 equal to 0, there's no x there. So there's no vertical asymptote. For the x-intercept, we set the numerator equal to 0, which is the 2x minus 1. And so 2x equals +1, and so x equals 1/2. And so 1/2, 0 is our x-intercept. And so that's about here. Okay, and so we don't have a horizontal asymptote or a vertical asymptote. And that happens anytime your function becomes linear, when you don't have any denominators anymore. There's no asymptotes, and so it just looks like a line with a hole in it. And so to graph the rest of this, we just graph it like we would any line. And so you can tell that the slope of this line is 2 and the y-intercept is 1. And so you can go up 2 over 1 to get more points if you wanted to, but honestly, we have enough. We already go up 2 over 1, up 2 over 1, up 2 over 1. So if you wanted to be super accurate, you could fill up the graph with points to make your line. Okay, and so you don't have to list all of these other points. We had enough to create the graph. But you can say none for asymptotes, none needed. And then for domain, we still have to skip over the whole. We still have to skip over the factor that makes the denominator 0, even though it canceled. And so we're skipping over the x value of -1. So our domain goes from -infinity to -1, pick back up on the other side, and go to infinity. All right, last example. And so before we factor, let's find the y things. So we're looking for the horizontal asymptote, and we're looking for the y-intercept. Okay, and so for the horizontal asymptote, looking at the degrees, we have degree 2 over degree 3. So it's bigger on bottom. And so that's the Bobo case. So y equals 0 is our horizontal asymptote. For the y-intercept, we're plugging in 0 for all the x's. So we get 0, 0, 0, 0. And so this would end up giving us -1 on top and a 0 on bottom. And we know that's undefined. And so there is no y-intercept. Okay, and so now we are ready to factor everything. And so the numerator is a difference of squares, x plus 1, x minus 1. And every term on bottom has an x, and so we need to factor that out. And then we have a quadratic that will factor. We need two numbers that multiply to -2 but add to 1. That's 2 and -1. Okay, and so there's our factor numerator and factor denominator. This time we have 3 factors in the denominator, and so be careful for that. And I see a common factor on top and bottom, x minus 1. And so immediately we know there's a whole. So we crossed off x minus 1, so that's what I'm setting equal to 0. And so x equals 1 is the x coordinate of the whole. And so our simplified function just has an x plus 1 on top, and then an x and an x plus 2 on bottom. That's what we're going to be working with for the rest of this example. And so we got to find the y value. And so x plus 1 on top, and then we have x, and then x plus 2. So we're filling in the 1 3 places. So 1, 1, 1. This is the simplified form. And so on top we end up with 2. On bottom we end up with 1 times 3. And so the y value is 2/3. And so 1, 2/3 is the coordinates for the whole. So we can graph that 1 2/3 almost to the 1. And then let's graph our horizontal asymptote at y equals 0. And then now we're ready to find the x things. And so we're looking for the vertical asymptote, which is our x equals asymptote. And then we're looking for our x-intercept, which is an ordered pair with y being 0. So for vertical asymptote, we set the denominator equal to 0. For x-intercept, we set the numerator equal to 0. So starting with the vertical asymptote, our denominator is x times x plus 2. And so we get one solution from the x, that means x equals 0. The other solution comes from the x plus 2, which means x equals -2. And so we have 2 vertical asymptotes, x equals 0, x equals -2. For the x-intercept, we're setting the numerator equal to 0. So we get x equals -1, and so -1, 0. Okay, and so putting our asymptotes on the graph first at x equals 0, and then also at x equals -2. I'm going to use blue to make that a little bit darker. Okay, and then we have an x-intercept at -1, 0. So that is right here. So this is another one of those weird cases where we cross the horizontal asymptote in the middle, but not on in the far end behavior. Okay, so to figure out what else is happening, we're gonna have to use some test points. We can already tell what's happening in the right quadrant for the most part. we can treat the whole like it's a point. So we're going to go up towards the vertical asymptote, down towards the horizontal asymptote. And we can assume that this isn't going to cross again because there's no more x-intercepts. We would have another x-intercept if it crossed the asymptote. And so now we need to figure out what is happening in the middle. And we also need to figure out what's happening on the left. Let's start with the left side because that's going to be a little bit easier. We're either going to have the function up here or it's going to be down here. Not both, otherwise it would fail the vertical line test. So one or the other. And so we just need to plug in one of these points to see if it's positive or negative. And so I'm going to plug in -3. You could do -4, -5, -10, whatever you want. I stick to close to the asymptote. And so using our simplified form is this boxed function here. And so x plus 1 is on top, and then we have x times x plus 2 on bottom. And so -3 goes 3 places. And so we have -2 on top, and we have a -3 times -1 on bottom, which is -2 over +3. And so -3, -2/3 is another point. Which would be about here. And so now we know the function is going up towards the asymptote, down towards the vertical asymptote. And so now we don't know what's happening in the middle. We have this point, but we don't know if it's going down and then continuously going down. We don't know if it goes down and comes back up. We don't know if it's going up and then down like this. And so we don't know. So we have to plug in a point on each side of this point. Okay, and so that's kind of annoying, and especially since they're not going to be whole numbers. But remember, we just need to know if it's positive or negative. We just need to know where it lands in relationship to the green asymptote. And so you don't have to number crunch all the way to the exact value. I just need to know if this point is up here or is it down here. And so these x values, this would be -1/2 and this would be -3/2 because this is our -1. And so we're going to plug in x equals -3/2 to the left, and then we're going to plug in x equals -1/2 to the right. Both into the simplified form. And so y equals x plus 1 over x times x plus 2. And we're plugging in -3/2, which is -1.5 if you would rather use the decimal. Okay, and so on top, -1.5 plus 1 would just be -0.5 or -1/2. I'll leave it as a decimal. And then on bottom, we get -1.5 times +0.5. And so I end up with a negative number over a negative number. This result would be negative. And so the final result, those negatives would cancel and be positive. And so because I know it's positive, I'm going to write it like this. Negative over negative is positive. We know at -3/2 it's going to be positive. So we know the function is going up on the left. And so now we're going to do the same thing for -1/2. And so this time y equals x plus 1, x, and then I'm always plugging it into this simplified form. That's where I'm getting this equation. And so -0.5, -0.5, let me use blue. Negative 1/2 is the same as negative 0.5 if you prefer the decimal. And so we end up with a positive 0.5 in the numerator. And then we still have this negative 0.5. And then this would become positive 1.5. And so we end up with a positive number on top. And then this result would be negative. And then positive over negative, put these y's here, our y value would be negative. Okay, and so at the negative 1/2, we know it's going to be below. That's where the negatives are. And so that means it's going down to the right. And so you don't have to include these in other points. If you wanted to, you could say negative 3/2 positive, and then negative 1/2 negative, to say how we figured out this behavior. Okay, and then lastly, the domain, we're still just skipping over the values that make the denominator 0. And so originally there were 3 factors, and so we still look at those 3 factors, whether they're wholes or whether they're vertical asymptotes. And so we're gonna have to skip over 0, we're gonna have to skip over negative 2, and then we're also gonna have to skip over positive 1. 0 and negative 2 are the vertical asymptotes. I'm going to put them in order. And then we have that whole at x equals 1. And so we're going to go in order. And so negative infinity, the first value we get to is negative 2. Pick back up on the other side of negative 2, and then we get stopped at 0. Pick back up at 0, and then we get stopped at 1. And then pick back up at 1 and go to infinity. And so what this looks like on the graph is negative infinity, and then we get stopped at the vertical asymptote, that's negative 2. And then we keep going, then we get stopped again at x equals 0. And then we keep going, and then we immediately get stopped again at the whole. And so 3 interruptions in our domain. The first 2, vertical asymptote, and then the 1 was the whole. All 3 made the denominator 0.